Okay. Okay. Viewers. Okay, I think I got everything up. There's too many screens, too many monitors to get everything going. So I'm going to go ahead and make this go live on LinkedIn. Oh, that's great. I wonder if I have to wait. Remote is good. Working on the preview. Okay. We'll try to go live. You say you're good. Try. Okay. Hopefully LinkedIn does well. Okay, we'll start in like 2 minutes. Feel free to say hello in the chat. Tell us where you're from. Talk about FPGAs. Your interest in Altera FPGAs, what applications you want to look at. So feel free to start adding comments to the chat. We'll address it in our breaks throughout the live stream. Okay. YouTube is happy? Is that too much? Oh yeah. YouTube is happy, Twitch is happy, and LinkedIn is happy. That is great. Um, okay. Okay. Welcome to this FPGA live stream. We're going to be covering Altera Agilex 7 Accelerator, a very basic accelerator, using an image convolution filter. And we're going to demonstrate this on real hardware. We'll start with the Agilex 7. If we got time at the end of the stream, I can redo the demo on the Max 10. But I am FPGA Zealot. You can find me on YouTube, Twitch, LinkedIn, apparently. You can use my Andrew Wilson ad for LinkedIn. But let's go ahead and talk more about what's happening today. So this is a sponsor stream by Altera. I am not employed by Altera. I do not offer official support for these products. And for the content of this channel is created for information purposes only, and the opinions are mine. But I would love to thank the sponsorship from Altera that gives an example to play with a really fancy Agilex 7 board. And today we're going to be looking at doing a very basic FPGA accelerator. For this example, we're only going to be using Quartus IP, specifically the platform designer. I want to demonstrate how you can rapidly prototype an existing accelerator with their kind of block level platform designer tools. We're going to do a basic one today with kind of JTAG driving everything, but you could easily look at Ethernet or JTAG or some other type of interface to bring in data in and out of your system, or like HDMI output for video. The source code is on GitHub. Let me go ahead and throw that in some of the links. So if you're watching, copy over. I have to do it from this side. Give me a second. if you have Quartus up and going, feel free to open the related project and walk along in Quartus. We have the source code available. I don't have a really good guide. I'm working on that, but you should be able to open the Quartus project, look at the platform design, and look at our Tickle Python that we're going to use to interface later of it. There's a Max 10 version of it, so if you have a Max 10 board, you can bring that up. And I'm going to try to get a more technical, detailed tutorial on Hackster IO in like 2 weeks. We'll see how that goes. So let's talk about our application that we're accelerating. We're going to be looking at an image convolution filter. So the best way to demonstrate this, there's a link in the description from this individual, Victor. And this is a great visual tutorial how a convolution works. And we'll kind of explain why convolutions are important for future applications that we're going to look at. We're going to be looking at FPGA AI suite that comes from Altera, and this is for deploying convolutional neural networks. And convolutional neural networks are a much more dramatic version. And so we're going to be digging more into that next time. But this time we're going to be doing a very basic convolutional filter over an image. So we have a grayscale image, and each pixel has, a value between 0 and 256, and we can, scroll over it. And using a convolution, we have what we call a kernel, and this kernel can be 3 by 3. It's usually 3 by 3 is the smallest. It's not really useful to go smaller than that, but it can be by 3 by 3, or it can be up to as big as you want. And when you go into convolutional neural networks, you can even have multi-dimensional kernels, which gets really fun. So, but here's the basic idea. So let's go to the identity. We're going to go to identity. So identity is basically a copy, which has a 1 in the middle. And what this does, so if we take like the corner here, it's going to take each pixel, multiply it by the coefficient in the kernel, add them up together, and that's going to be the new pixel in the output. You can see on the output, we now have a black border because we've now processed the image, and if we don't account for the edge, the images will actually compress by like 1 pixel around. So this is a basic identity. Now we go to something more interesting like a blur. So this blur is taking data from the neighbor pixels. So if we go here, it's going to take the different data from the neighbors, basically multiplying it by these coefficients, these weights, and getting us a value. And this isn't, the blur is kind of a basic thing, but we can do some more interesting things like an emboss right here. But for edge detection, we can do Sobel filter. We can do a bottom, left, right, or top Sobel. We'll do a left Sobel right here. And this basically does edge detection from left to right. This image is kind of pixelated, but we can go down to a more complex image here, where we can do Sobel. So like if we can look at our identity, we can look at blur. The blur is not dramatic with 3 by 3. If we increased it like 8 or 8, the blur would be a lot more dramatic. And then we can do the Sobel from the left. We can do a Sobel from the top. And then the sharpen. You can kind of see how the edges are feel like a little thicker. My favorite is outline. I just like. It's not useful for edge detection, but it gives a nice visualization of processing the image. But this is used in image processing, video processing, and convolutional networks. And we're going to demonstrate how we're going to use this in Altera FPGA. So here's kind of an example of how convolutions work in a CNN, a convolutional neural network. This is MIMNIS, probably one of the most basic convolutional neural networks there is. And you have your basic input image, which is smaller than your normal image. It's only 32 by 32. And then there's several convolutions that divide it into different layers. And see, each layer has a different size kernel that's using to process the image with several different, different kernels for each layer. And basically, when you train an AI, you're taking those coefficients in the kernel and you're using back propagation to define what those coefficients in the kernel are. So for image processing, we manually place in the coefficients. For neural networks, we're using training, usually on GPU, and backpropagation for basically using complex math to define the coefficients to match what we want on the output through the training process. More about neural networks later. Today we're going to focus on image processing. So we're going to go ahead and go from scratch and build a basic platform designer to go through the system. Talking for now. Okay. Go here. Call it examples to follow what we're doing already. Let me get the correct version of the board. I can never remember the huge long report. So we're going to go to Agilex 7. Put in this. So next we're going to change some basic device options to support our specific Agilex 7. Once again, the Agilex 7 has an option to have the kind of the power definition built into the hardware. You can look at the previous video about this. So there's kind of like a power management bus. It's built into the FPGA. And for this particular dev board, the FPGA on bring up will define the power sequencing. We're just going to put in the correct settings for that. Okay. And then we're going to bring up platform designer. Ooh, quick breather. So, welcome to the stream. If you're new, we're starting to look at a custom accelerator inside of Quartus within the platform designer. Thank you for joining us. This is a sponsor stream by Altera to kind of demonstrate the Agilex 7 Quartus and its advanced features that we'll look later, like FPGA AI suite. And today we're looking at a basic image processor using that Quartus IP. So if you have any questions, feel free to talk and chat. We have chat for LinkedIn. We have chat. We have chat in LinkedIn, chat for Twitch, and chat for YouTube. We have some questions. So for this stream, we're not going to be discussing any comparisons of Altera versus other FPGAs. We're going to be focusing on the Altera application. If you want to talk more about other FPGAs, feel free to join the Discord in the chat, or join the Discord that's in the thing. And we have different conversations for those different vendors on the Discord server. Okay. Oh, open up platform designer. I'm gonna check that on LinkedIn to make sure this is going as I expect. I'm not seeing any chats on LinkedIn. I just want to make sure that it's okay. Looks like it's running. Okay. So now we're going to open up, yes, platform designer, and we're going to walk through the steps of how to get a JTAG level system going. Okay. So for this, we're going to call the top level DMA top. Okay. Someone asked Twitch if the outline kernel is popular. It's not that it's popular. It's not really useful. I just enjoy using it. Mike. The audio should be coming through. Can we have a mic check? Can everyone hear me? Sorry if I stopped talking for a second. Okay. Cool. So we're going to start with our basic clock and a basic reset. For this system, we're going to set up our clock to 100 megahertz. We're going to set our reset to an active low reset. And then we're going to add the reset release. And this is basically holds this basically there we go. This basically holds the system in reset, soft design, until the FPGA is ready to go. So we'll add that. So next we're going to add the JTAG to Avalon Master Bridge. And we're going to connect the clock reset. So next we're going to do the system ID. The system ID provides like a known value. We're going to use this to make sure that we are connected to the correct machine, correct FPGA. Do clock. We're going to bring in the reset from the JTAG device here. Okay, and then bring in the JTAG. Okay, so we're going to need some memory in this system. So we're going to go ahead and add some on-chip memory. And for this, we're going to need at least 256 kilobytes. This is just going to be useful to be 2 image size wide to be able to do it input buffer and an output buffer. We're going to connect the JTAG master to that. So next, we're going to look at our actual accelerator. So the accelerator is called a 2D FIR in this system. And this is probably the more complex one we have to configure. So, okay. Hopefully you can see well enough. We're going to do one color plane. So we're going to do grayscale image. We're not going to do RGB or anything like that. We're going to do one color plane. We're going to do 4 pixels at a time. So this basically is going to equal 32 bits, which is important. We're going to set up 400 by 320. We're going to do 8 pixels standard FIR. We're going to go to 3. No mirroring. We're going to do sine coefficient, which is going to be basically it's going to be a 2's complement of an 8-bit fixed point value with yeah, that's we're going to do runtime control. This allows us to change the alpha channels or the coefficients or the weights how you like. We're going to remove the need for user packets. And we're going to say video has no blanking. Normally, if you have like raw DVI or VGA video, you're going to have a space in the horizontal and the vertical for blanking. We're dealing with just raw data here, especially the image, just an image. So we're going to remove blanking. And clock reset and control. Okay, so next we're going to talk about DMA. So the best DMA controller here is going to be the modular scatter gather DMA. This is a rather complex system, so we're just going to do some basic features about it. And we'll talk about how we enable those features later. So let's open this up and we're going to look at it. So for this situation, the 2D FIR filter is using a streaming sink and a streaming source. So we're going to go memory map to streaming. And we're going to change maximum length to 128. You may do larger if you want to do, like, a larger image. And the other features we're going to look at is packet support enable. And that should be everything we need. And then we're going to duplicate this. And we're just going to change this to streaming to memory mapped. So we have our basic DMA and Accelerator. Add some resets. Someone asked in the YouTube chat if this is going to be recorded. Yes, this will be a VOD recording on YouTube, Twitch, or LinkedIn. So feel free to jump in wherever you want to be able to view this in real time. Or not view it in real time, but you can view it after the fact. Okay, so descriptors. The control and the descriptor control system are going to go to the JTAG master. Okay, before we move on, I just want to welcome anyone to the chat. Where we are doing a stream today on doing a FIR filter in the FPGA. And if you're new, feel free to say something in the chat. We are doing a sponsor stream from Altera on the Agilex 7 today, and you can also repeat this on the Max 10. And let me look at the chat real quick. We have some questions about block RAM and fixed point data. So yes, this Intel on-chip memory is basically a wrapper around some internal block memory. The fixed point data is not for the image, it's for the kernel. So this is the coefficients. These are going to, well, I'll show you later. You'll see it in the demo where we're going to take these coefficients and use it to modify the image stream while it's being processed. Okay. Okay, next is a little of the confusing part. So we have DMA out video and DMA in. But if we take, let's add that here, that there. But if we try to take this source and stick it to the D in here, we're going to get a little error right here where the read latency doesn't match. So to address this is probably the most, we're going to look at the Avalon streaming adapter. Now I'm just going to go through these settings. Basically, we're going to set up the 32 bits and turn everything off. Use empty port. That's going to be relay in C1. So we finish this. Now we have this adapter. We move this adapter up here. We can have the stream source go to the adapter and the out and go to the system. And we shouldn't have a latency issue. Did we not turn packet? Use packet. There we go. And add the clock. Reset. Okay, now we're gonna duplicate this adapter for the other end, and then we should be done with mostly done with our system. And this one we're going to put this is 0, this. Now we should be able to go from D out in here and out, I think. Okay, we're almost done with the boring part. We can actually do some more interesting stuff. Okay. Did that. Oh, do I need a use packet? Okay, let me just make sure. So we're going to look at here. Let's start a packet. Okay, this does use packet. There we go. Start a packet, good. Start a packet, that's good. Okay, cool. So all we need to do now is assign the base addresses. Okay. So we're going to go to that. Let's go to the address menu. I just want to make sure the addresses match what I expect. Okay. 4860, that's good. And on-chip memory is there. This is at 4000, okay. 0, 50, or no, 250, yep, and 40. Wait. Oh, this control, this one is 460, 0, and 40. Okay, that lines up. Cool. Everything's happy. We don't have any interrupts to use, so we don't need to connect those. Let's go ahead and save it, and we'll build it. Then I'm going to show you how to add a signal tap to design. We're going to generate the song. Okay. So, thank you for joining this live session. I hope many people have an opportunity to view the recording. How many of you actually have a Max 10 or Aria 10, Cyclone 5 or 10 or Agilex board available? And which one are you actually looking at? Because I feel educational wise, right, or hobby wise, you usually have a Max 10, Cyclone 5, or Cyclo 10. That's just, because of the licensing. With the Agilex 5, it'd be interesting what hobby board is available for the Agilex 5, because you're going to be able to get a free pro license for it, which would be really cool. So, Cyclone and Max 10. I should be able to, probably do a poll sometime and talk about which boards are available. So there is the Max 10 version on the GitHub. It's basically the same design. I had to reduce the VRAM utilization or the on-chip memory size to fit into the Max 10 and then reduce the resolution of the image. Okay, so we're going to close this. We have a design. Files, right? We're going to set this as top level. We're going to go ahead and do analysis and synthesis. We can go ahead and apply the pinout. Let me go look that up quick. Okay, cool. Whew. Let's see how latency is doing. which actually seems to be the slowest moment. LinkedIn seems actually relative low latency. It's interesting how these streams line up using this multi-stream broadcasting system. Okay, while this is building, we can take a moment and look at the hardware we have. So on screen, we have the Agilex 7 that is a relatively robust the SoC development board because it has the the hard processing system on it, and it has a lot of QSFP connections. It has two FMC connections, fully populated FMC connections, which is amazing. Then it has like a PCIe over MCIO. It has some fancy high-speed transceiver connectors as well. On the very bottom, we have the Aero Max 10 board. Unfortunately, it's not being produced right now. If you do find it on eBay, it goes between like $25 and $35. Great little board to pick up. On the bottom right, we have an Aria 10. This you can actually find on eBay. It's called the Hawkeye. It's about, you can find it between $60 and $90 off of eBay. The most expensive part about that is actually getting the Altera JTAG programmer. If you already have the official Altera programmer, it's relatively easy to pick up this Aria 10 board. And so these are the boards I use as targets for the demo today. Okay, so first we're going to go ahead and actually add the pins. This shouldn't take but a moment. Then we're going to look at the signal tap and be able to get the D in and D out going. So this is going to be AE52. We're going to say the IO stand for this is true differential. And then the reset, we're going to do AE53. That's all we need to do. Okay. And then for the signal tap, we're just going to go for a default selection. There is an Avalon stream interface, but I need to look more into how this works. But for now, we're going to do a simple interface which gives us enough information. Okay. Oh, sorry. Let's get back to the correct scene. So we have opened up the signal tap inserter for Quartus, and we're going to be looking at adding, I guess, debug signals, internal scope into our inputs and outputs of our 2D FIR filter for the image processing. Okay, so the easiest way to do this is we're going to focus in on the FIR filter. We're going to add some wildcards with D in. Open this up bigger. See all our little options. So when you do this, you'll get a bunch of internal signals. And if we go all the way to the bottom, or the short ones, these right here are the outputs, are like on the very input and output of the system. So we're going to grab all of the in signals, bring it over to the right, and redefine this as D out. Search. Scroll all the bottom to the very top level IO. Grab all the D out related signals and insert. Okay, now we can close this. And we have our different signals. Right now I'm going to take the valid and change that to a rising edge flag, and we can look at this later. The next thing is the clock. That's the same thing. We're just going to zoom in here. We're going to see if there's a clock we can grab. And we're just going to do main clock. Good. So we are set up. So we're going to save this to the top level of the project. I'm just going to call this STPST to match the example project on GitHub. We're going to enable it, and we're ready to go. So what we're going to do is we're going to basically restart the compilation. This may yell at you real quick because it didn't properly enable the STP. You may have to just like re-hit assemble. We'll see what happens. Okay, it's doing good. Okay, it seems to be happy. So we already have this up and running. And we're going to go ahead and load it up. So if you have the GitHub project, and if you built the Agilex 7, see how well can you actually see this on the screen? Yeah. There will be a SOF file here, and we're going to go ahead and through the tickle shell and Quartus, we're going to program that to the FPGA. Let's go ahead and power on the FPGA. I'm going to pull up a file that helped me demo. Of Okay, so we have programmed the FPGA. Now we need to interact with that JTAG master. So let's pull up that. Why that comes out. So you can do this through what's called the system console. This allows us to connect to different JTAG interfaces. I'm going to pull up the platform design again so you can see what's happening. Okay. This is where it becomes a little fun. We're going to be looking at some low-level command line here. So, when we create our JTAG to Avalon master, we basically create a JTAG level interface to do reads and writes to the FPGA. If we do this, we see that there are two PHY masters. The first one right here is a 10M device, which is located on the Agilex SFC device. Second one is the Agilex master PHY. So this right here is the Max 10 that acts as the system controller, and right here is the Agilex bus. So to interact with that, we're going to create a variable in Tickle. There we go. So we're going to create a variable, which is MSP. And we now have, so if we do a puts, do $MSP, we now have the Agilex device. The next thing we're going to do is we're going to open up a service master to this. And now we can do basic reads and writes. And there we go. This is our ID. So let's go ahead and demonstrate that, where this is, what's happening here again. So I'm going to pull up. Okay, while it's opening up, I just want to say hello to anyone who's joining us in the stream. We're currently looking at the Agilex 7 FPGA and doing some image processing. This is a sponsor stream from Altera, and I am FPGA Zealot. You can find me on YouTube, Twitch, and LinkedIn. and Twitter, or X Twitter. And today we're going to go through a fun demo to do some image processing on the FPGA. If you want to leave any comments, you can do it on LinkedIn, Twitch, or YouTube. And thanks for those who have commented. It's great to see the interaction. If you want to go back and look at something, we're going to have some moments to review some of the material. So feel free to ask questions as we go further. So, back to this. Make sure the screen is good. Okay. So, when we got the JTAG PHY right here, this JTAG PHY, that is using this JTAG to Avalon master bridge. And basically what we're doing is going down this master, and we're doing reads and writes. So right now, we're going to see if we can bring the, here we go. Then from the name. So we can go down here and through this tickle interface, so we can read these different addresses. And we just read this address here, which is the sys ID, which is translated to Cafe Taco. So that's just demonstrating a basic read to the system. That's not going to be useful for a demonstration, so we're going to do a little trick I have. And this is basically, we're going to do a telnet connection over tickle. And this basically comes from here. And we're basically going to start a server, and it's going to capture ASCII commands, run them, and then return the results. We also added a few basic utilities because it's hard to use variables. For this, we're basically going to have the variables be local to the tickle script. This is on GitHub. If you want to go look at it, it's basically a simple interface to do a telnet connection to your tickle server. And from there, we're going to use Python to do telnet. And this is even a smaller file. We're just basically going to open up a socket and do ASCII input and output over this socket. And because this is telnet, we can potentially do this remotely. You don't have to be local. In this situation, we're going to use local only. And then we have an IPython notebook that we're going to use to interact with this system. Okay, so the server's up and running. So if you want, you can open this in the GitHub and scroll as you want. But in the beginning, we have a few variables that will help you specify your target. So you should be able to run this script no matter which FPGA example that's available. So we have a target for 0, 1. This is just choosing which JTAG bus is available. If you have a more complex JTAG by setup, you're going to have to kind of go through, but I'll show you how you can verify this is correct. And then the resolution of your image. And that's basically everything else is going to be static for the setup. We get the size of the image, and then these are some base addresses that we're going to use for our read and write buffer for DMA. So we have programmed the FPGA, we have set up the tickle system, or the tickle telnet. Now we're going to connect to this, and we're going to go ahead and open the bus. So, oh, sorry, did I not run this? Okay, let's run that. Okay. Thank you for subscribing. So now, when we open the bus, we now have a new target for the Agilex device. And we can go ahead and do a basic read of the system ID. Okay. Now, we're going to be writing some Python driver software to interface with the IP cores. To follow along, you can, when you, in the platform designer, you can pull up this documentation. So let's pop up the platform. I want to interact. So I have this 2D fur filter, and I want to interact with the control bus. If I go to details, you can't see it in the window here. So if I go to details, I get this window in the middle. And oh, it's Avalon. Sorry. We're going to go here to the top of the IP core. Click details. And here we have a user guide. When we open this user guide, it's going to go to the same location for the 2D4i filter. So if you need to know more information, you can always just follow the links in the Quartus tools. So we're going to go to the control registers. And I'm not going to go over each address right now, but I'm going to focus on what's important. For us, we're going to look at the control register, which is a single bit. That is a go bit. That's all we need to do for that. And then we have a coefficient commit that says that the next clock cycle, we're going to load in our coefficient data. And then the coefficient data, that's each of our coefficients, our weights, what you would want to call them, those fixed point values. And each register is going to have its own fixed point value. So now we go back to our Python. These are the addresses. So this is the base address for our IP core. So we go to system view right here, the base address right here. And then these are the register offsets that are located here. So this is incrementally by word. So we're going to have to increment that by 4x here. Basically kind of writing our own basic driver software for this. I assume that the Neos 5 and Neos 2 have their own driver software somewhere, but we're not going to reference that today. And then we have our different examples we can look at. So we can dig into this a little bit, but basically this allows us to input a NumPy 3x3 array as a kernel, and then load these different values into the kernel. And basically I'm translating the float to a uint16. Or a fixed point uint16. This is kind of my basic, we can just put a comma here, right? Float to fixed point. We're going to commit. Well, now we have the arrays. Let's go ahead and run these. And this is basically, right here we have our test kernel, and we're going to load in the identity matrix. Okay, so we're going to get, it's a little bit complex here, just because it's kind of hard to follow what's happening in the documentation. But the easiest way to show this is actually to bring up that signal tab that we were working on earlier. So let's go ahead and set this up. Set up right here. Okay, so we're going to go ahead and get ready to acquire. And then we're going to look at the data for this. I just don't want to forget to do that. Okay, so once again, we have documentation for the control packets that are going through our system. You're going to have to dig down into this, but basically we have to define the width and height of our video resolution over the AccuStream filter before we can begin processing. And in this situation, we have a resolution X, a resolution Y. We're going to take the nibbles. We're going to divide each of these values into 4 nibbles. And then using this format right here, you can kind of see it better here. We're going to divide those nibbles into some packets. And then we have our header, which is F, and our end, which is kind of just empty. Or interlacing, which we were doing a 3 on. Okay. And we're going to set up the config packet. And here we can actually look at the raw config packet in the system. So there's our beginning flag, our 190 resolution, our 140 or our 190 width, or 140 height, and then that's the interlacing value. And then we have a basic DMA system. And once again, I mean, we could probably dig more into this, but once again, for the descriptor, we have 4 addresses: read, write, length, and control. And I kind of just define base address here, the register offsets, and then some control bit offsets. So we're going to use control go, control start a packet, control end a packet. And using a basic reading of the control packet at address 0. The control packet at address 0, we're going to send this small packet over the AXI stream. A lot of words, but let's actually run it and see what happens. Okay. So our signal tap triggered. You can't see much because we're zoomed out and we can see a large portion of the system. So what we're going to do is we're going to zoom in. And basically, here we have the F, the 190, the 140, and the 3. That's our small control packet we are sending to the system. I'm glad you all are still listening. This has been a lot of verbal description of register, driver, explanation. But hopefully, if you do this, you can follow the steps in the video and make sure you see the same exact packet format. And then you can read the documentation if you want to do more complex configurations and descriptors for the DMA. So it gives you a good starting point. And anyone who has joined us, welcome to the stream. We're looking at the Agilex 7 FPGA. Let's go ahead and bring up the... we're looking at the Agilex 7 FPGA and doing image convolution on it. This is a sponsored stream from Altera. Feel free to watch on LinkedIn, Twitch, or YouTube. The latency across them seems to be fluctuating a little bit. Right now, YouTube is doing the best. Say hi in the chat, tell where you're from, and if you have any questions on the stream. Right now, we're going over the live demo. Okay. Video's good, audio, chat, everyone looks good. I'm glad people are watching. The chat's been kind of quiet a while, but it looks like we still have some good numbers. Okay, here comes the fun part. We want to set up continuous reads and writes over DMA. So we have a DMA stream, or DMA to stream base address, and a stream to DMA base address. So this is going from DMA to stream to filter to back to the memory map, back to our memory. This is basically doing a continuous read and write that's going to go through our FPGA accelerator. So the only thing we're adding is right here. We have 2 new control bits on the DMA, and it's called pack read and pack write. And this will basically repeat the last descriptor until a new descriptor is added to the DMA core. This allows us to do continuous reads and continue writes. We're going to go ahead and get this running. And now if we do a signal tap again, and we zoom out, we can see that we have continuous data being processed. That's a little descriptor right here. And zoom in on that portion. So if we zoom on this portion right here, we can actually see there's a little descriptor. We have F19143, F1943, and then it goes through and does the actual data. So right now, we're sending a bunch of zeros. We're reading zeros and we're writing zeros. So let's make this more interesting. So what we're going to do, well, you can't see anything, it's all zeros. This is reading the read buffer, reading the write buffer, it's all zeros. That's a print progress bar, it's a little utility. But let's go ahead and we're just going to do incrementing values based upon the address in the system. Take a few seconds. So now we have written incrementing addresses, and we can see a few addresses here. It's not really useful in this situation, but let's go ahead back to signal tap. We're going to reacquire the data, and now we have incrementing values. So we look at the incrementing values. We can see that we go up to 1, F3, FC. So basically, the entire size of the image. And we can have a relatively continuous stream. You can see that the ready and valid aren't high every single cycle, but we are doing 4 pixels at a time. And what's a good point? Let's look at the full size. I just want to kind of iterate how this is a accelerator. So our design is using less than 1% of the Agilex 7 FPGA. So it would be easy to increase the clock speed, increase the resolution, increase the parallelization of the system to dramatically improve this accelerator. But this gives a basic example that's really easy to scale up. Okay. So go back and do some more interesting things. So we were doing an identity matrix before, right? So up here we had an identity matrix, 1. So now we're going to do half of an identity matrix with 0.5. I'll load this up, and it's basically instantly done. And we have the input here, and once again we have the output, and we go from a hex 14 to 10, and the hex 14 is 20 to 10. So we're basically dividing the image in half. And once again, I mean, I don't think you're going to see anything terribly interesting on here. We can zoom in at the end here, and we can see that we divided. It was 1F, now it's 1/7. Well, okay. That's how the pixels work. Okay. While incrementing numbers are a useful way to have expected inputs and expected outputs, let's do a more interesting test step. Okay. And before we before we dig into the Python portion of this, if there's anyone new to the stream, thank you for joining. We're looking at image filtering on the Altera Agilex 7 FPGA. This is a sponsored Altera stream, and I am FPGA Zealot. You can find me on X, YouTube, Twitch, LinkedIn. Follow the stream. You can watch it later. Feel free to ask questions, join the Discord. There's a GitHub with all the source. And you can leave any comments or questions in any of our chats. And thank you for those who are still continuing to watch. Hopefully we can finish up here and then explore how much we're accelerating this situation, and maybe take a moment to go do it on the max 10 FPGA and show how easy it is to change it up. Okay, so next we're going to be using OpenCV. This is an open source image library for Python, and we can load up a image. And this image is a height of, yeah, that's going to be what, like 1119, maybe 1200, maybe 1200. No, it's definitely 1100. So we then can resize it. Resize it for 400 by 320, so it fits our input. And then we're going to write these to the system. Basically, we're translating the raw data into ASCII using a string format, and we're going to pack it. We're going to take the 4 pixels at a time, and we're going to pack it together. And then we're going to write this once at a time. Okay. We have a little progress bar to watch it being written to the image. And then we're going to create a blank image of all zeros. So we have a new variable, a new pointer, new allocation of memory. And then we're going to read that image from the system. And basically we use the read command, take the hex value, convert it to an integer, and then do some byte, unpack the bytes into each pixel. And then we can display the gray scale image. And we have processed a identity, well, identity divided by 2. Can you just tell anything? You can see it's a little grayer everywhere. The only reason this is slow is because we're using JTAG to ASCII to Telnet to Tickle to our Python JTAG interface, which is really slow. But this is almost instantly happening on the FPGA. We'll calculate how fast it's at the end. So let's go ahead and change this. So here, this is going to be our left Sobel right here. We're going to then implement our left Sobel into our 2D filter. So instantly change the filter, basically, and instantly compute the thing. Now we're going to reread a new image from the device. And feel free to subscribe, leave a like, follow me on any of these platforms for more stuff about FPGAs in general, but excited to continue doing more Altera, Agilex, FPGA, looking at AI tools in the future. Let me rerun this. Okay, so now we have a left Sobel on the image. Okay, so this one is the outline. This is the one I like a lot. We can also do a custom one. We'll do emboss next. We'll do emboss on the last one. That'll be a fun one. So we're gonna go ahead and do the outline, read the image. And there's our outline. So this is a very basic image, right? We have very sharp edges, very simple logo. Let's go ahead and do a more complex image. Here is a picture of the Altera HQ from years back. We're now going to write that image. We add the new filter here. I want to do the emboss. This should be at DWC. How about there? Okay, that works. Okay, let's go read. So this should be a basic outline. While that's loading, let's look up what the emboss is going to be. It's going to be -2, 1, 1, 1, 1, 2. Okay, we'll add that in a second. Okay, so here's our outlined image. Yeah, a little bit better. Okay, let's go emboss that image. And then make these all line up so it's easy to see. There's our emboss filter. Now we're going to load another image and read it. Did not like embossing that image, did it? Let's try the emboss on this image. So load it, size it, write the image, and I want to see what the embossing looks like on that. Okay. Yeah, it doesn't really like that embossing. -2, 1, 1. Yeah, maybe the image just isn't bright enough. You can kind of see it. Okay, let's see. Is there something else worth trying? I guess we could try sharpen. Yeah, let's try to sharpen. That's gonna be interesting. 5. Go ahead and reload this image while we're doing that. Okay. Okay, so the name of the board in the top right corner, that's the Intel Agilex 7 F-Tile SoC development board. Go ahead and add that as a comment for you. Wait for the fly. I have to get that link up here. There you go. Okay. Interesting. Like the sharpen should work. Oh, I can't go above. I got okay, I know what to do now. So we can do emboss like this. So the way we did the fixed point, we can't go above 2. We can only go basically up to 1. So if we do this, okay, now I know what I'm doing. Okay. So the way we did the fixed point values, right? So if we go back here to the filter right here, we did this over so you guys can see. We did fixed points. And we only have 1 integer. We can't go above 2. If we wanted to, we could have done, like 8-bit integer bits and 8-bit fraction points, and we could have done a lot more. But we're just doing this. Okay, thank you. There's our embossed image. It's what I expect. Okay, let's go ahead and do sharpen. And to do that, we're going to do a 1 in the middle, do a 0.2 here. 0.2. So okay. Now this should give us a sharpened image. Okay, there is our sharpened image. It's kind of dark. What we can do is we can upgrade this to 1.8, and we should have a probably not oversaturated. Okay, there, a better sharpened image. And this how I guess it does look sharper, right? Can we like put this in the new image? Not really. Now we can copy the clipboard. But you can kind of see it looks a little cleaner on the lines, which is interesting. Okay, so let's talk about how we're accelerating here, right? So we do time.time. That gives us like our time start. Ends, right? Ends. End my start. Cool, almost instant. Now let's add filtering. So we're going to use OpenCV. So we're going to use my computer to do the filtering, and we're going to look how long it takes. Do I need to... Oh, no. Doing that instantly. Somehow I don't believe that. What's the best way? We need a better way to find Python. Okay. Maybe there's something in the cache happening in the background. I guess we could... Okay, let's go below. We're going to print out... Make sure it's working as expected. Okay. Maybe it's just cheats. Might be too smart for its own code. That's better. Okay, let's try this method. I want to be able to time it, and it's not instantaneous. Hi, John. Okay. Welcome to everyone's stream. We've kind of gone through the demo. I'm trying to measure the time on my processor versus the FPGA. But thank you for joining us. We're looking at image processing on the Altera Agilex 7 FPGA. This is a sponsor stream from Altera. You can find the source code for this on GitHub in the comments. Feel free to ask questions in the chat on LinkedIn, Twitch, or YouTube. Feel free to leave a like or subscribe or anything like that as well, as that will help spread information about this system. And I'm trying to measure this, and my computer is telling me it's instantaneously doing it, and I don't believe it. Okay, I like that. That's better. I assume time it is returning the seconds. Okay, the default timer returns as a float. Okay, and if we go like that. Oh. So that's 5 seconds. And if I do 1, we get this. Okay, we can do this. I can work with this. So this is seconds. So if we times this, right, we're going to say micro milliseconds, micro nano. So this is going to be microseconds. If we then do what format? crazy. How do we bring that down? Okay, now times it by 1,000 for milliseconds, times it by 1,000 for microseconds. So this takes 121 microseconds. So if we do 1,000, 1,000, we'll just say this. Okay, it's going to run. It should give us basically the microseconds of the thing. Oh. Should run for 2 minutes. Oh, okay. While that's working, let's figure out the math. So the clock for our system is going to be 100 microseconds. And so our period will be 1 over clock. And we need to do width. Well, we have size. Well, we do like this. Width times height equals size. So we're also doing 4 pixels at a time. So size. So I am doing this backwards. Size equals this. And then per clock size, or per clock data is going to equal size divided by 4 because we're doing 4 pixels at a time. Oh, okay, we're able to do that in 60 microseconds. So this is going to be so if we do print per clock data times clock or period. Sorry. I'm using my GPU or something of it. Okay, so it should be on the order of 32 microseconds. And so we do period. Okay. That's it. No. Okay. Well, that would be nanoseconds. Right, missing. Oh, it is 10. This is going to be 10 nanoseconds. Okay, not 1 nanosecond, 10 nanoseconds. Okay, so this is the same thing for the max 10, but we can look at this. We do the same, modifier. How's this come out? It should be 32. Okay. So currently the processor is beating us, but we could easily bump this up to 50. and we could probably bump this up to 16 pixels or greater or something like that. So if we actually did a more comprehensive design on the Agilex 7, we could beat my more expensive processor and system. And we could definitely do much better bandwidth and latency over the system. Okay. So let's go ahead. Is anyone interested in looking at the Max 10 setup? I mean, it's going to be identical. I guess we can run it real quick. It won't hurt. I wonder if this changes. No. I wonder if this changes if we this time changes if we go something like this. Okay. Let's go ahead and set up the Max 10 FPGA so everyone can look at that. Have to, because you guys can watch me do this. Okay. So for the Max 10, we're going to use these ports. Cable. Got the Max 10 hooked up. So we're going to go change over to the Max 10 image and demonstrate what this can do. How that runs. Okay. Exit system console here. So in this system, we are in the Agilex 7, so we're just going to go up the Max 10 demo. Does this have an output files? It might not. Yeah, this is just on the it's an output file. Okay, so let's go ahead and program the Max 10, which is pretty instantaneous. This is still running. See what this number is before I change it. Okay. So while that's running, we can do a quick recap. Hello, welcome to join the stream if you're new. We're almost done with the stream, but thank you for joining anyways for the live portion of it. We're looking at the Altera FPGA. We looked at the Agilex 7, showing how to do a basic image convolution on it. Now we're going to do the same demo on a Max 10 FPGA. And this is a sponsor stream from Altera. We're demonstrating how to prototype FPGA Accelerator within Cordis. We're doing a very basic one, but it's still allows the Max 10 to compete with my processor, which is really cool. And it's great for low latency. If I had a video output on the Max 10 working, that'd be actually really cool. We could plug in a camera, have the video output. I'll work on getting that running, and maybe I can do another post a video about that. But we're gonna go ahead and jump onto the Max 10 and just kind of run through the demo real quick, but that will be the end of our stream. If you want to look at the video, we show how to set this up with Platform Designer. I'll use a single tap to look at the signals, how the IP works, how to interface with the IP at a register bit level, and then demonstrate through kind of like a live JTAG debug how we can do this with various FPGAs. Okay, this ran, so that was longer, but not much longer. Okay, so we're gonna go ahead and close this, and we're gonna reestablish it over here, and then we're gonna go up to the top. We're going to do kernel reset, clear all outputs, so everything's new. Set up to 1,000, and So we're going to change this to a 0 to max our max 10 target. Change the resolution to 320 by 200. And then we're just going to do run all cells. And scroll to the top, and we'll just walk it running. So we have the max 10, 50 DA. We're able to read the ID code. We set up the system. Where's the interesting part? Here is the incrementing values we added. We had the half filter, and we go from 20 to 10 in hex. And then we have the real demo working. Or going faster than I can like scroll. Here we go. You can see it actually loading up real quick, doing the identity matrix. Here we're doing a Sobel, a left Sobel filter. Boom, done. Then we'll do the outline. Loading the new one, and then we'll do a sharpen. So here we go. We got running on the Max 10. You don't hear the fan of my Agilex 7. So this is a simple enough accelerator that you can do it on a Max 10 FPGA, but also using the same IP on a Agilex 7, you can demonstrate it. To make this more impressive, trying to look at the sharpen. Yeah. To make this more impressive, we could use video, PCIe, or Ethernet, or something like that to transmit data back and forth. Did I do an extra one there? Yeah. Oh yeah, much smaller size helps a lot. In this situation, we're beating the processor. I guess technically this is only a 15 megahertz clock, so in tech it's like that. But yeah, look at Max 10 is able to process on like scale with the processor. Okay, yeah. So that's it for the stream. Feel free to look at this recording on LinkedIn, Twitch, YouTube. Feel free to leave your like and subscribe. Do we have any questions, comments to close out? I just want to once again iterate that this is I want to thank Altera for this sponsorship for the stream and the board. We're going to be looking at the FPGA AI tools in a few weeks, probably 2 to 3 weeks, actually 3 weeks. And we'll be doing more complex Agilex 7 level examples. This was just a very basic example that you can repeat on any FPGA system that you want to know. Feel free to go to the GitHub, build the examples, run them on your local hardware. If you have any issues, use a Git issue. If you have any further questions, you can go to the Discord in the description. And we go ahead and talk more about Altera, FPGA accelerators, and maybe I can show how to get the PCIe video or something else up later. Okay. Okay. I just want to thank you again for watching, and I'll give you guys like 3 minutes before I close up. Oh yeah, we can go back here. Find me on with FPGA Zealot on these media sources, and we'll look at more complex accelerator variants. Maybe not as sponsored streams, but at least through GitHub or some social posts, we'll talk about more complex examples and make the source code available. And look out for the Hackster.io article doing a more technical deep dive into what we did today. I'm waiting for Twitch to update. Okay. Well, I guess I'll see you guys next time. Thank you for watching. Bye.